Hello everyone, this is Priyanka KS studying at Sri Venkateshwara College of Engineering. My USN is 1VE22IS040. Today in this video we'll be knowing about additional list operations, sparse matrices and doubly linked list. First we'll know what is list operations. List operations consist of node where each node contains a data, field and reference to the next node in a list. There are various linked list operations that allow us to perform different actions on linked list. For example, the insertion operation adds a new element to the linked list. Here's a list of basic linked list operations. Traversal access each element of the linked list. Insertion adds a new element to the linked list. Deletion removes the existing element from the linked list. Search helps to find the node in the linked list. Sort the node of the linked list. Next, we'll move into additional list operations. Additional list operations are the functions and methods that can be used to manipulate and modify singly linked list. There are also additional list operations include sorting, merging, reversing, and searching. These operations can be implemented using various algorithms and data structures. Traversing of a list. Traversing of a list refers to the accessing of each element of the linked list. Traversing allows to read each element in the list. It can also be done in one direction, and this process can be used to print the elements on the list. Pointer points to the next node to be processed. Traversing also can be done using loop or recursion process. For example, displaying the contents of the linked list is very simple. We keep moving the temp node to the next one and display its contents. When temp is null, temp refers to temporary. We know that we have reached the end of the linked list, so we get out of the while loop. Next, we'll move on to searching of an element in the linked list. Searching is used to search an element in the list. Searching is similar to traversing as it can also be done in one direction. Searching involves comparing each node. Searching involves comparing each node value with the value we are searching for. We have an algorithm for searching of an element in the linked list. First, we have to start from the head node and compare the values of the current node with the target value. If found, the element can perform desired action. Else not matched, move to the next node by updating the current node to the next in the list and repeat the steps until you reach the end of the list. For example, we can create a linked list with some elements and define a search method in the linked list class. The method traverses through the list, comparing each node's data with the element we want to find. If a match is found, we return true, indicating that element is present in the list. Otherwise, we return false, like indicating element is not present in the linked list. Next, we'll move on to inserting of an element in the linked list. Insertion refers to adding of a new element to the linked list. Inserting can be done from the beginning of the linked list and middle of the linked list, and also from the end of the linked list. Now we have an algorithms for all three from beginning, end, and from the middle. Now we'll see beginning. Insert at the beginning, allocate memory for a new node, store data, change the node to the point to head, change head to point to recently created one. Next, insert at the end, allocate memory for new node, store the data, and travels to the last node. Change to the next node to the recently created node. Next, we'll move on to the deletion of an element from the linked list. Deletion refers to deleting of elements from the linked list. Deletion also can be done in two ways, that is, from the beginning and from the ending. Firstly, we have to start from the head node and keep a track of the current node and the previous node. Traverse through the linked list until you find the node with the element you want to delete. Once you find the node, update the reference of the previous node to skip the node you want to delete. This effectively removes the node from the linked list. If the node you want to delete is the head node, update the head node to the next node in the list. Free the memory allocated for the node you want to delete. Deleting an element from the beginning points ahead to the second node. Deleting from the end traverse to the second last element changes its pointer to null. You have to remember that deleting a node from the linked list requires updating the references correctly to maintain the integrity of the list. Now we can see the deletion from the front. Deletion from the front. Firstly, we are assigning the first node to temp, and we are checking the first node equals to null. That we are checking the list is currently empty at the beginning. If the list is empty, then we'll print list is empty. Or else next, if the list is not empty, we are printing the deleted element from the list, making the second node as the first node and deleting the first node. We'll move on to the sparse matrix. Sparse matrix is defined with a two-dimensional array. An array with m rows and n columns represent m into n matrix. There are many situations in which matrix contains more number of zero value than non-zero value. Such a matrix is known as sparse matrix. Sparse matrix is a matrix which contains a very few non-zero elements. They are commonly used to represent data that is mostly empty or sparse. Sparse matrices can also be stored efficiently using different data structures such as linked list, arrays, or dictionaries. In other words, sparse matrix can be defined as the matrix that has a greater number of zero elements than the non-zero elements. There are few benefits using sparse matrices, that is storage and computing time. Storage, we know that sparse matrix contains lesser non-zero elements than zero elements. So less memory can be used to store elements. It evaluates only the non-zero elements. Then computing time. Computing time in the case of searching in the sparse matrix, we need to traverse only the non-zero elements rather than traversing all the sparse matrix elements. It saves computing time by logically designing a data structure traversing non-zero elements. Basically, where a sparse matrix save memory by only storing non-zero elements, reducing storage requirements, and a list format stores each non-zero element with its row and column indices. Sparse column format stores the non-zero elements column wise with auxiliary arrays. Array representation of sparse matrix. Array representation of a sparse matrix is done by 2D array leads to the wastage of lots of memory. This is because zeros in the matrix are of no use. So storing of zero with non-zero elements is a wastage of memory. To avoid such wastage, we can store only non-zero elements. If we store only non-zero elements, it reduces the storage and can save the traversal time and storage space. In array representation of sparse matrix, row indicates it is the index of a row where a new non-zero element is located in the matrix. Column is the index of the column where a non-zero element is located in the matrix. Next, the value is the value of the non-zero element that is located in the index, that is of row and column. Next, we'll move on to singly linked list representation. In this, row indicates index of row where non-zero element is located. Column indicates index of column where non-zero element is located. And value of the non-zero element is located at index. Next node, address of the next node. Next, we'll move on to doubly linked list. Doubly linked list is a special type of linked list in which each node contains a pointer to the previous node as well as the next node of the linked list. This allows for efficient traversal in both directions. Doubly linked lists are commonly used when operations like insertion and deletion needs to be performed at both the ends of the list. In doubly linked list, each link of a linked list can store a data called an element. Next indicates each link of the linked list contains a link to the next link called next. Previous, each link of the linked list contains a link to the previous link called PREV, that is previous. Linked list indicates a linked list contains the connection to the first link called first and the last link called last. Here are few applications of doubly linked list. It is used by web browsers for backward and forward navigation of web pages that are LRU least recently used or MRU most recently used. Catch are constructed using doubly linked list. Whereas applications to maintain undo and redo functionalities. A doubly linked list is maintained by thread scheduler to keep track of processes that are executed at the time. Here are few advantages and disadvantages of doubly linked list. Doubly linked list can be traversed in both forward and backward directions. The delete operations in doubly linked list is more efficient if a pointer to the node to be deleted is given. We can quickly insert a new node before a given node. In singly linked list, to delete a node, a pointer to the previous node is needed. To get this previous node, sometimes the list is traversed. In doubly linked list, we can get the previous node using the pointer previous. Disadvantages of a doubly linked list are every node of a doubly linked list requires extra space of a previous pointer. It is possible to implement doubly linked list with a single pointer also. All operations require an extra pointer previous to be maintained. For example, in insertion, we need to modify previous pointers together with the next pointers. And also for the example for following functions for functions at different positions, we need one or two extra steps to set previous pointer.